50 Physics Ideas You Really Need to Know by Joanne Baker. This is an independent educational overview enriched with our own integrative analysis and actionable exercises. Think of it as a guided reflection to spark your own insights, not a replacement for reading the book itself. Chapter 1. Mach's Principle. A child whirling on a merry-go-round experiences an outward pull, an effect Mach's principle attributes to the gravitational influence of distant stars. This concept suggests that mass in the cosmos fundamentally impacts local inertia and motion, asserting that movement is meaningful only when observed relative to other objects, not against an unmoving absolute space. Just as discerning which train is moving at a station can be ambiguous, Ernst Mach posited that motion isn't with respect to a fixed grid, as Isaac Newton believed, but rather determined by the entire universe's distribution of matter. Mass, defined as the quantity of matter an object contains, and convertible to energy, and inertia, its inherent resistance to changes in motion, are profoundly linked to this cosmic web of gravitational interactions. Newton's famous spinning bucket experiment, which he saw as proof of absolute rotation, was reinterpreted by Mach. Without external references like distant stars, an object's true rotation is undeterminable. All motion is relative. This groundbreaking idea that motion is always relative to other matter deeply influenced Albert Einstein's theories of relativity, reshaping our fundamental understanding of space and its relationship to motion and forces. Hill number 2. Newton's Laws of Motion. Isaac Newton, a colossal figure in the history of science, unraveled fundamental truths about motion that govern everything from a thrown baseball to the orbits of planets. His 3 revolutionary laws explain why objects move, accelerate, and react to forces, forming the bedrock of classical physics and providing insights into phenomena like a golf ball's curving path or a stunt rider defying gravity on a vertical wall. Newton's first law introduces the principle of inertia. An object at rest stays at rest, and an object in motion continues in motion with the same speed and in the same direction, unless acted upon by an external force. This explains why a space probe, unimpeded by friction, maintains its trajectory, while a hockey puck on ice eventually slows due to unseen resistive forces. His second law quantifies this change, stating that the force applied to an object directly determines its acceleration, inversely proportional to its mass, F equals ma. This means heavier objects require greater force to achieve the same acceleration. Galileo's famous thought experiment, famously confirmed on the moon by Apollo astronauts, demonstrates that a feather and a hammer fall at the same rate in a vacuum because gravity imparts the same acceleration to both, irrespective of their mass. Finally, Newton's third law reveals the interplay of forces. For every action, there is an equal and opposite reaction. When one roller skater pushes another, both move apart due to these reciprocal forces. This principle explains the kickback of a rifle or the pressure a stunt rider feels against an inclined wall, demonstrating how forces are always paired. These laws provided a comprehensive framework for understanding motion, explaining the dynamics of everything from simple falls to complex engineering feats, even if later discoveries by Einstein unveiled their limits at extremely high speeds or for very small masses. Chapter 3. Kepler's Laws. Johannes Kepler, a profound observer of the cosmos in the late 16th and early 17th centuries, sought to uncover the hidden mathematical patterns governing the universe. He meticulously analyzed astronomical data, particularly the intricate, seemingly backward loops of Mars's movement across the sky, phenomena known as retrograde motions that had long puzzled astronomers. Prior models, like Ptolemy's Earth-centered universe, attempted to explain these with complex epicycles, while Copernicus's sun-centered model, though revolutionary, still relied on perfectly circular orbits. Kepler, initially driven by a mystical belief in perfect geometric forms underlying nature, used the highly accurate observational tables compiled by Tycho Brahe. His groundbreaking insight came from realizing that planetary orbits were not circular, but elliptical, with the Sun positioned at one of the ellipse's two focal points. This fundamental discovery shattered the long-held notion of perfect circular celestial paths. From this revelation, Kepler formulated three seminal laws describing planetary motion. First law: planets orbit the Sun in elliptical paths, not circles, with the Sun located at one focus of the ellipse. Second law: as a planet traverses its elliptical orbit, an imaginary line connecting it to the Sun sweeps out equal areas in equal intervals of time. This implies that planets move faster when they are closer to the Sun and slower when they are farther away. Third law: the square of a planet's orbital period, the time it takes to complete one orbit, is directly proportional to the cube of the semi-major axis of its elliptical orbit. In simpler terms, planets farther from the Sun take disproportionately longer to complete an orbit. For instance, a planet twice as distant would take roughly 8 times longer to orbit. Kepler's laws provided a comprehensive and accurate description of all planetary orbits within our solar system, and indeed for any celestial body orbiting another. Although he had uncovered the how of planetary motion, the why remained elusive, until Isaac Newton later unified these geometric descriptions into his universal theory of gravitation. Chapter 4: Newton's Law of Gravitation. Isaac Newton made a profound intellectual leap, uniting the seemingly disparate motions of falling terrestrial objects like apples and cannonballs with the celestial dance of planets and moons. He proposed that all bodies attract each other through an unseen force, gravity. The strength of this force is proportional to each object's mass, but diminishes rapidly, specifically by the square of the distance between them. This universal law explained how the Moon constantly falls towards Earth, yet remains in orbit, much like a cannonball fired with immense speed, endlessly circling the globe as the planet curves away beneath it. This inverse square law elegantly unified Johannes Kepler's planetary observations and explained phenomena from the predictable orbits of comets to the ebb and flow of ocean tides, which arise from the Moon's differential pull on Earth's near and far sides. Though immensely powerful and a cornerstone of physics, Newtonian gravity finds its limits in regions of extreme gravitational strength, paving the way for later theories like Einstein's general relativity. 05. Conservation of energy. Energy is an animating force that causes movement and change, appearing in many forms like height, speed, heat, or waves. Though its intrinsic nature remains elusive to physicists, it is understood as a fundamental property of matter and space, a drive capable of creating or changing. A cornerstone of physics is the principle of energy conservation. Energy cannot be created or destroyed, only transformed from one type to another, maintaining a constant total amount. Galileo first observed this exchange in a swinging pendulum, where gravitational potential energy, due to height, converts into kinetic energy of motion and vice versa. This principle extends to various energy manifestations, including elastic energy in a compressed spring, heat from atomic vibrations, electromagnetic waves like light, and chemical energy. Einstein further expanded this by demonstrating that mass itself represents stored energy, described by E = mc², revealing the immense energy released when mass is transformed. While we speak of generating energy, we are actually transforming it, often from solar-derived sources, like fossil fuels, into electricity. Beyond energy, physics also upholds the conservation of linear momentum, mass times velocity, conserved in collisions, and angular momentum, important for spinning objects like ice skaters, both essential tenets applicable across modern physics. Simple harmonic motion. Many vibrations in the natural world adopt simple harmonic motion, a predictable and stable oscillatory pattern. This motion occurs when an object displaced from its resting position experiences a correcting force directly proportional to its displacement and always acting in the opposite direction. Consequently, the object swings back and forth, overshooting its equilibrium point before being drawn back, akin to the rhythmic bounce on a well-sprung bed. The classic pendulum beautifully illustrates SHM. As it swings, the pendulum bob continuously swaps gravitational potential energy for kinetic energy, moving slowest at the extremities of its arc and fastest through its center. The projection of this circular motion onto a line, like the shadow of a child's swing seat, reveals a sine wave pattern over time. A particularly compelling demonstration is the Foucault pendulum, which proves the Earth's rotation. While its swing plane remains fixed in space, the Earth rotates beneath it, causing the pendulum's observed plane of swing to slowly turn throughout the day, a phenomenon most pronounced at the poles and absent at the equator. Pendulums have also been instrumental in timekeeping for centuries, their accuracy dependent on their length, as famously maintained in Big Ben's precise adjustments. Simple harmonic motion extends far beyond pendulums, manifesting in oscillating currents within electrical circuits, the fluid movement of particles in water waves, and even the vibrations of atoms in the early universe. While inherently stable, SHM can be profoundly affected by external forces. When these driving forces synchronize with a system's natural oscillation frequencies, a phenomenon known as resonance occurs, significantly amplifying the vibrations. This powerful effect was tragically showcased by the Tacoma-Narrows Bridge, nicknamed Galloping Gertie. In 1940, strong winds induced twisting oscillations that matched the bridge's resonant frequency, leading to its dramatic and catastrophic collapse. Such amplified vibrations can rapidly become erratic or even chaotic, demonstrating how easily the foundational stability of simple harmonic motion can be disrupted by subtle, resonant interactions. Hooke's law. Hooke's law, originally derived from observations of watch springs, articulates a fundamental principle. Elastic materials deform proportionally to the force applied. This means if you pull an elastic object twice as hard, it stretches twice as far. Materials obeying this law are elastic because they reversibly return to their original shape once forces are removed, within certain limits. The inherent stiffness of a material, known as its elastic modulus, dictates how much force is needed to achieve a certain stretch, defining the relationship between stress, applied force per unit area, and strain, percentage increase in length. This principle underpins countless applications, from ensuring the safety of bungee jumpers to the structural integrity of buildings. Most critically, it revolutionized navigation. In the 17th and 18th centuries, accurately determining longitude at sea was a significant challenge, as existing pendulum clocks were ineffective on unstable ships. British watchmaker John Harrison, building upon the understanding of elastic springs, engineered the chronometer. He ingeniously compensated for temperature-induced changes in spring elasticity by incorporating a bimetallic strip, ultimately winning a substantial prize and solving the critical longitude problem. Robert Hooke, a prolific polymath whose contributions spanned astronomy, biology, coining the term cell, and architecture, remains paradoxically remembered mostly for this one law, despite his profound and wide-ranging impact. 8. Ideal gas law. The pressure, volume, and temperature of a gas are intrinsically linked, a fundamental relationship quantified by the ideal gas law. This principle helps explain everyday phenomena, from the efficient cooking of food in a pressure cooker to the difficulties of boiling water at high altitudes. Formulated as PV equals nRT, the law states that pressure, P, multiplied by volume equals the number of moles of gas, N, multiplied by the gas constant, R, and the temperature. A mole represents a specific, immense quantity of atoms or molecules, approximately 6 × 10 to the 23rd, also known as Avogadro's number. An ideal gas, the theoretical model described by this law, is composed of very small, widely spaced particles that engage in perfectly elastic collisions, meaning they bounce off each other and container walls cleanly without losing energy or sticking. There are no additional attractive or repulsive forces between these particles. Noble gases like neon and argon and light symmetrical molecules such as hydrogen closely approximate ideal gas behavior. The law demonstrates that reducing a gas's volume by half effectively doubles its pressure. And similarly, doubling its temperature will also double its pressure. This occurs because increased temperature translates to faster-moving particles hitting container walls with greater force, while reduced volume leads to more frequent collisions. Pressure cookers leverage this by trapping steam, increasing internal pressure to raise the water's boiling point above 100 degrees Celsius, thereby cooking food more quickly. Conversely, at high altitudes, lower atmospheric pressure causes water to boil at a much lower temperature, making cooking more challenging, a situation famously noted by Charles Darwin when his potatoes remained stubbornly hard in the Andes. Chapter 9. Second Law of Thermodynamics. The second law of thermodynamics stands as a fundamental pillar of modern physics, dictating that heat invariably flows from hotter bodies to colder ones, never the reverse. At its heart, this law is inextricably linked to the concept of entropy, which quantifies disorder within a system. Simply put, for any isolated system, entropy, or disorder, always increases over time. This principle doesn't just govern everyday phenomena, it's tied to the very progression of time, the unfolding of events, and even the ultimate destiny of the universe. Consider the simple act of adding hot coffee to ice. The ice melts, the coffee cools, and eventually the temperature evens out. This universal tendency reflects the second law, preventing heat from concentrating itself and making temperatures more extreme. While refrigerators appear to defy this by cooling objects, they do so only by expelling a greater amount of heat into their surroundings. Thus, when the entire system, refrigerator and environment, is considered, the overall entropy still increases, upholding the law. Entropy itself describes the number of ways items can arrange themselves. A neatly organized stack of spaghetti has low entropy due to its order, but once cooked and tangled, its disorder, and thus its entropy, increases. Similarly, the universe, as a vast isolated system, inexorably moves towards a state of maximum entropy. This implies that over billions of years, its matter will disperse, stars will fade, and galaxies will tear apart, leading to a uniform, featureless heat death, a blended soup of particles where all distinct structures have dissolved into ultimate disorder. This fundamental law also shatters the age-old dream of perpetual motion machines. Since any process converting heat into other forms of energy inevitably involves some loss, an increase in overall entropy, no engine can run forever without external input. Even thought experiments, like Maxwell's demon attempting to sort molecules to create temperature differences, ultimately fail because the act of observation and sorting also requires energy, ensuring that the total entropy of the system and its surroundings always climbs. The second law remains an unbreakable constraint on the mechanics of our universe. Chapter 10. Absolute Zero. Absolute zero marks the theoretical point where a substance's atoms cease all motion, a state never truly reached in nature or laboratories. Temperature itself quantifies the average energy of these particles, their speed in fluids or vibration in solids. As matter cools, atomic movement diminishes, progressively nearing this hypothetical stillness. This concept led to the Kelvin temperature scale, which defines absolute zero at negative 273.15 degrees Celsius, negative 459.67 degrees Fahrenheit, and serves as the scientific standard for temperature measurement. Remarkably, scientists have engineered conditions within billions of a Kelvin from absolute zero using advanced techniques like laser cooling and specialized liquid helium mixtures. In the universe, the Boomerang Nebula, at 1 Kelvin, holds the record for coldest natural temperature, yet still remains above absolute zero due to pervasive cosmic background radiation, 2.7 K. Ultimately, reaching or definitively measuring absolute zero faces fundamental limitations. Any instrument would introduce heat, and at such extreme low energies, quantum mechanics profoundly alters atomic behavior, making its absolute attainment an enduring challenge. 11. Brownian motion. The erratic, jiggling movement of tiny particles suspended in a fluid, known as Brownian motion, reveals the invisible dance of molecules. 19th-century botanist Robert Brown first observed pollen grains twitching under his microscope, realizing they were not alive but constantly buffeted by surrounding water molecules. These incessant, random collisions create a slight force imbalance, causing the particle to embark on an unpredictable random walk, a jagged, staggering path that cannot be forecast in advance. This phenomenon affects any small particle in a liquid or gas, with more vigorous movement occurring when molecules are heavier or hotter. Albert Einstein later provided the mathematical framework in 1905, offering compelling proof for the existence of atoms and molecules. Brownian motion is fundamental to diffusion, the process by which concentrated substances gradually spread out to form a diffuse cloud, even without stirring or currents. This mechanism explains the dispersal of pollutants and aerosols through air or water. The unpredictable pathways of Brownian motion are also intrinsically linked to fractals, unique patterns that exhibit self-similarity across all scales. Coined by Benoit Mandelbrot, fractals are shapes that look essentially the same whether viewed up close or from afar, like coastlines, tree branches, or snowflakes. The mathematics of Brownian motion can generate these fractal patterns, proving valuable in computer graphics for landscapes, spatial mapping for robotics, and medical imaging for complex body structures. Furthermore, the principles of random movements help predict outcomes of numerous random events, finding applications in modeling stock market fluctuations, floods, and social processes like manufacturing and decision-making. Chapter 12. Chaos Theory. Chaos theory explores how minuscule shifts in initial conditions can lead to vastly different outcomes over time, famously dubbed the butterfly effect. While seemingly random, chaotic systems are in fact deterministic, Their behavior is governed by fixed rules, making them reproducible if exact starting points are known. However, their extreme sensitivity means that even unmeasurable differences in inputs can trigger entirely divergent paths, rendering long-term prediction impossible. Weather exemplifies this, where a tiny atmospheric alteration can evolve into a major storm elsewhere, limiting forecasting accuracy to mere days. Edward Lorenz pioneered this field in the 1960s, discovering that even slight numerical rounding in his weather models produced dramatically different simulations. He observed that while specific outcomes were unpredictable, the system's behavior was confined to certain patterns, or attractors, often appearing as complex, fractal-like structures, like the Lorenz attractor resembling butterfly wings. This principle extends beyond weather to phenomena such as billiard ball trajectories and the unstable orbits of celestial bodies, demonstrating chaos as a fundamental and widespread aspect of nature. The orderly arrangements we perceive, even in our solar system, might be the stable remnants of past chaotic interactions. Chapter 13: Bernoulli Equation. The Bernoulli equation describes the fundamental relationship between a fluid's speed and its pressure. Faster-moving fluids exert lower pressure. This principle profoundly explains phenomena ranging from aircraft lift to blood flow within the human body. Observing a narrowing jet of water from a tap illustrates this effect, where the water accelerates and its pressure drops, causing it to constrict. Pioneering this insight, Daniel Bernoulli discovered that this pressure drop is proportional to the fluid's velocity squared. This concept illuminates why airplanes fly. Air moving faster over the curved upper surface of a wing creates lower pressure there than on the flatter underside, generating lift. In medicine, constricted arteries cause blood to speed up, leading to a pressure drop that can produce turbulent flow, identifiable as heart murmurs or even risk collapsing the vessel wall. Similarly, carburetors use this effect to draw fuel into an engine. Bernoulli's understanding originated from applying the conservation of energy to fluids, a principle that continues to model diverse fluid behaviors, from ocean currents to weather patterns. Chapter 14: Newton's Theory of Color. The familiar beauty of a rainbow finds its scientific explanation in the pioneering work of Isaac Newton. He demonstrated that white light, when passed through a glass prism, separates into a vibrant spectrum of colors: red, orange, yellow, green, blue, indigo, and violet. This proved that these hues were intrinsic components of white light itself, rather than being created or imprinted by the prism, an idea that profoundly reshaped scientific understanding despite initial contention. Newton's experiments in the 1660s revealed that these individual colors, once isolated, could not be further split by additional prisms, and conversely, they could be recombined to form white light. This challenged prevailing beliefs, such as those championed by his contemporary, Robert Hooke, who argued that colors arose from mixtures of white light and darkness, or were mere imprints. Newton also clarified that objects appear colored because they selectively reflect specific wavelengths of light. For example, a red sofa reflects primarily red light while absorbing others. Thus, its perceived color is a consequence of its interaction with light, not an inherent quality. For Newton, understanding color was a gateway to comprehending the fundamental physics of light. He initially hypothesized that light behaved like waves, similar to water, made of minute corpuscles. This particle-wave duality was later refined. Light was discovered to be electromagnetic waves. Yet elements of Newton's particle concept resurfaced when Albert Einstein later showed that light can indeed behave as energy-carrying particles called photons in certain contexts. Light waves are specifically transverse waves, meaning their disturbance, changes in electric and magnetic fields, is perpendicular to their direction of travel, differentiating them from longitudinal waves like sound. Newton systematically arranged the spectrum's colors into a circular color wheel, demonstrating how primary colors, red, yellow, blue, combine to create others, and how complementary colors, such as blue and orange, positioned opposite each other, achieve maximum contrast. This innovation became an invaluable tool for artists. Later, Johann Wolfgang von Goethe expanded on this concept, adding magenta to the wheel and noting that shadows often take on the complementary hue of the illuminated object. Each distinct color of light corresponds to a different wavelength within the vast electromagnetic spectrum. Prisms separate white light because each wavelength is refracted, bent at a unique angle. Red light, with the longest wavelength, bends the least, while blue light, with the shortest, bends the most, thus producing the rainbow sequence. Visible light, while crucial for human perception, represents only a small segment of the spectrum. Beyond visible red lie longer wavelengths like infrared, carrying heat, microwaves, and radio waves. Beyond visible blue lie shorter wavelengths such as ultraviolet light, which can damage skin, X-rays, used in medicine, and gamma rays. Our eyes have evolved to be sensitive to visible light because its wavelengths interact significantly with atoms and molecules. Chapter 15. Huygens' Principle. Imagine dropping a stone into a still pond, producing expanding circular ripples. Dutch physicist Christian Huygens devised a powerful tool to predict wave behavior, Huygens' principle. This concept posits that every point on an advancing wavefront acts as a fresh source of secondary wavelets. These individual wavelets then combine to form the wave's new position, effectively propagating its movement. By repeatedly applying this idea, one can trace a wave's evolution, even around obstacles or during reflection. If you visualize a wavefront, drawing numerous small circles from points along its edge and then sketching a tangent line across their outer boundaries reveals the wave's next position. Essential wave properties like frequency, the number of cycles per unit time, and phase, a specific point within a cycle, such as a crest or trough, are conserved in these new wavelets. This principle elegantly explains various wave phenomena. When ocean waves pass through a narrow harbor opening, they diffract, spreading out into arcs, because only a short segment passes through, acting as new sources. This spreading reduces a wave's concentrated force, as observed with the 2004 Sumatra tsunami, which lost energy diffracting around islands. Similarly, when you shout into another room, the sound seems to emanate from the doorway itself. The doorway effectively becomes the new source of sound waves, erasing the original room's specific acoustic history. Huygens' principle also describes reflection, where a wave hitting an edge generates inverted circular ripples propagating backward, and refraction, the bending of waves as they move into a medium that changes their speed, like ocean waves entering shallower water. Despite its predictive power, Huygens' principle has a theoretical limitation. It predicts both forward and backward wave propagation, yet waves only move forward. Huygens himself simply disregarded the backward wave, acknowledging it as a practical tool rather than a complete theoretical law. Beyond his principle, Christian Huygens was a prodigious 17th-century scientist, discovering Saturn's rings, which he correctly deduced were made of countless small orbiting bodies, and its largest moon, Titan. Centuries later, the Cassini-Huygens probe landed on Titan, exploring its unique landscape of liquid methane, a world where Huygens' principles still apply to its exotic waves. Chapter 16. Snell's Law. Snell's law illuminates the captivating phenomenon of light bending as it traverses from one material into another, a process known as refraction. This occurs because light travels at different speeds through various media, such as air versus water, causing its path to subtly shift. This fundamental principle explains common optical illusions, like a drinking straw appearing bent in a glass of water, or why a person's legs might look shortened when standing in a swimming pool. Even the illusion of shimmering puddles on a hot road is a result of light rays bending as they pass through layers of air with differing densities. The degree to which light bends is quantified by a material's refractive index. This value represents the ratio of light speed in a vacuum to its speed within that specific material. Denser substances, which slow light more significantly, possess a higher refractive index, leading to a greater bending effect. This property is critical in the design of optical instruments, from corrective lenses to sophisticated telescopes. Interestingly, refraction isn't unique to light. Ocean waves also demonstrate this behavior, slowing and bending as they encounter shallower waters near the shore. A related concept is total internal reflection, which occurs when light traveling from a material of higher refractive index to one of lower refractive index strikes the boundary at an angle too shallow to pass through. Instead, the light is entirely reflected back into the denser material. At its core, Snell's law is a manifestation of Fermat's principle of least time, which asserts that light rays invariably follow the quickest possible path through any medium. This inherent efficiency dictates light's journey, ensuring that rays taking the fastest route are reinforced, forming a coherent beam. Building upon these principles, contemporary physicists are engineering metamaterials, synthetic substances designed to exhibit extraordinary optical properties, including a negative refractive index. These innovative materials can bend light in ways previously unimagined, paving the way for groundbreaking applications such as superlenses that achieve unprecedented image clarity, and even cloaking devices capable of rendering objects invisible to certain electromagnetic waves. Chapter 17. Bragg's Law. Bragg's law explains how waves, particularly X-rays, passing through an ordered solid, like a crystal, produce distinctive patterns. This phenomenon, known as X-ray crystallography, allows us to deduce the hidden architecture of crystalline materials. All waves diffract, spreading as they encounter obstacles, or apertures. Think of light bending around your hand to create a fuzzy shadow. When X-rays, with their exceptionally tiny wavelengths, are directed through the regular lattice-like arrangement of atoms in a crystal, they scatter. The key to Bragg's law lies in interference, where these scattered rays interact. When the peaks and troughs of the X-ray waves align, they are in phase, they reinforce each other, producing bright spots on a detector. Conversely, if they are misaligned, out of phase, they cancel out. The specific arrangement and spacing of these bright spots directly reveal the distances and orientations of the atomic layers within the crystal. Mathematically, this relationship is expressed as 2d sine theta equals n lambda, linking the layer spacing, d, incident angle, theta, wavelength, lambda, and an integer. This powerful technique provided scientists with an unprecedented tool to visualize matter's deep structure. Its most celebrated application came in 1953, when it unveiled the iconic double helix structure of DNA, a discovery that revolutionized biology. Today, X-ray crystallography remains indispensable in materials science, chemistry, and biology for determining molecular architectures. Furthermore, the principles underlying Bragg's law form the bedrock for many modern medical imaging technologies, including CT scans, MRI, and PET, enabling us to peer into the complexities of the human body and advance both health and scientific understanding. Chapter 18. Fraunhofer diffraction. Fraunhofer diffraction describes the fundamental blurring of images that occurs when light from distant sources passes through an aperture, such as the pupil of an eye or a camera lens. This phenomenon explains why even perfect optical systems have a natural resolution limit, known as the diffraction limit. As light waves travel through an aperture, they spread out and interfere with one another. While most waves pass straight through, forming a clear central spot, others interfere to create alternating dark and light bands at the edges. The width of this central spot dictates the finest detail an optical system can resolve, scaling with the light's wavelength. Bluer light yields sharper images, and inversely with the aperture size. Larger apertures reduce blurring. When the aperture is circular, as in eyes and many lenses, these patterns appear as concentric, airy rings. In contrast, Fresnel diffraction occurs when the light source is close, leading to curved wavefronts and irregularly spaced interference patterns. Joseph von Fraunhofer also advanced the study of diffraction by creating gratings with multiple slits, intensifying interference effects. 19. Doppler effect. The Doppler effect describes the observed change in a wave's frequency as its source moves relative to an observer. This phenomenon is commonly heard in the rising pitch of an approaching ambulance siren, which then drops as it recedes. As the source moves closer, its waves are compressed, leading to a higher frequency. Conversely, as it moves away, the waves spread out, resulting in a lower frequency. This principle applies to all types of waves, including sound and light. Practically, the Doppler effect is utilized in measuring vehicle speeds by radar and monitoring blood flow in medical diagnostics. In astronomy, light from celestial bodies moving towards us exhibits a blue shift, higher frequency, while light from those moving away shows a red shift, lower frequency. This allows scientists to detect extrasolar planets by observing the subtle gravitational wobble of their host stars, which manifests as a periodic Doppler shift in the star's light. It's important to distinguish this from cosmological redshift, which is caused by the expansion of space itself, stretching light waves from distant galaxies, rather than the galaxies actively moving through space. Christian Doppler first described this effect in 1842, and its applications continue to expand our understanding of motion across the universe. Chapter 20, Ohm's Law. The unseen forces of electricity govern our world, explaining everything from the safety of an airplane in a thunderstorm to how your home's light bulbs maintain their brilliance. At its heart, electricity is the movement of electric charge, a fundamental property of subatomic particles like negatively charged electrons and positively charged protons. These charges interact through electromagnetic fields, and while charge cannot be created or destroyed, it can be moved around. Electricity can manifest as static electricity, a buildup of charges like rubbing a comb on a sleeve, or the spectacular discharge of lightning during a storm. More commonly, we encounter electric current, which is the steady flow of charge, typically electrons, through materials called conductors, such as metals. Insulators, like ceramics or plastics, resist this flow, while semiconductors allow it under specific conditions. Just as a river flows down a gravitational slope, an electric current is driven by a difference in electrical potential, known as voltage, which provides energy to the moving charges. However, charges don't move unhindered. They encounter resistance, which limits current size and converts electrical energy into heat. Understanding resistance is key to safety. Standing on an insulator can protect you from lightning, as can sheltering within a Faraday cage. This principle, demonstrated by Michael Faraday, explains why metal structures, like planes and cars, offer protection during electrical storms. The charge flows around the exterior, leaving the interior neutral. Benjamin Franklin's lightning conductor applies this by providing a low-resistance path, diverting lightning safely to the ground. Electrical flows move in complete loops called circuits. Analogous to water flowing through pipes, current is like flow speed, voltage like water pressure, and resistance like pipe width. George Ohm's pivotal law, published in 1826, algebraically states V equals IR, meaning voltage drop V equals the product of current I and resistance. This implies that voltage is proportional to current and resistance are inversely related. When light bulbs are connected in a series circuit, adding more resistance causes them all to dim as voltage is split. However, connecting them in a parallel circuit allows each bulb to experience the full voltage, maintaining brightness, illustrating how Ohm's law helps interpret complex electrical systems. 21. Fleming's right-hand rule. Electromagnetic induction, a fascinating phenomenon, explains how a changing magnetic field moving past a wire coil generates an electrical current, as seen in a bicycle dynamo. The faster this relative motion occurs, the stronger the induced current. To determine the direction of this current, Fleming's right-hand rule provides a memorable guide. Point your thumb in the direction of conductor motion, your forefinger in the direction of the magnetic field, and your middle finger will then indicate the induced current. This foundational principle was discovered by Michael Faraday, who also played a pivotal role in unifying various forms of electricity. His law quantifies the induced electromotive force, while Lenz's law ensures the induced current always opposes the change that created it, upholding the conservation of energy. Beyond dynamos, induction powers transformers, which efficiently adjust voltage for power grids, and influences capacitors, which store electrical charge, measured in farads, in circuits, from camera flashes to early Leyden jars, modulating current flow by their charging and discharging actions. Chapter 22. Maxwell's Equations. Maxwell's four equations stand as a foundational pillar of modern physics, eloquently describing the profound unity of electric and magnetic fields. They reveal that these phenomena are not separate, but rather two manifestations of the same underlying event, the electromagnetic wave. While early 19th century experimenters observed the interconversion of electricity and magnetism, James Clerk Maxwell provided the comprehensive mathematical framework that elegantly integrated them. Electromagnetic waves consist of a varying electric field accompanied by a similarly varying magnetic field, oriented at right angles to one another. Maxwell famously demonstrated that these waves travel at a constant speed in a vacuum, precisely the speed of light, thereby confirming that light itself is a propagating electromagnetic disturbance. This electromagnetic spectrum encompasses a vast range from long radio waves to visible light, X-rays, and gamma rays, serving as the basis for modern communications, heating applications, and medical imaging. The electromagnetic force articulated through these fields is one of the four fundamental forces, crucial for holding atoms and molecules together. Maxwell's revolutionary work consolidated the complexities of electromagnetism into four concise equations. The first, Gauss's law, characterizes electric fields, illustrating that their strength diminishes with the inverse square of the distance from a charged object. The second equation describes magnetic fields, asserting that their field lines always form closed loops, thus implying the non-existence of isolated magnetic monopoles. The third and fourth equations address electromagnetic induction. The third explains how changing electric currents produce magnetic fields, while the fourth, known as Faraday's law, details how changing magnetic fields generate electric currents. This monumental unification not only advanced physics immeasurably, but also laid crucial groundwork for Albert Einstein's theories of relativity, which further demonstrated how electricity and magnetism appear differently depending on an observer's frame of reference. Chapter 23. Planck's Law. The common observation that objects glow with different colors when heated, from red to yellow to brilliant white, holds a profound secret about the nature of energy and light. Max Planck masterfully connected the physics of heat and illumination to explain this phenomenon, laying the groundwork for quantum physics by re-envisioning light not as a continuous wave, but as discrete statistical units. When substances are heated, they emit light that changes in color as their temperature rises. A low heat might produce a dull red glow, as seen in barbecue coals. As temperatures escalate to thousands of degrees, like molten steel or a light bulb filament, the emitted light progresses through orange, yellow, and eventually to white, then even blue-white, indicating the addition of higher frequency blue light to the spectrum. This consistent pattern of emitted light, irrespective of the material, is known as black-body radiation. Intriguingly, darker materials are superior at both absorbing and radiating heat, explaining why black surfaces are used in stoves, or why hot climates favor white buildings. 19th-century physicists struggled to theoretically model black-body radiation curves, which consistently showed a peak intensity at a specific frequency that shifted with temperature. Classical physics, notably the Rayleigh-Jeans law, predicted an ever-increasing emission of energy at higher frequencies, leading to the infamous ultraviolet catastrophe, an absurd scenario where objects would radiate infinite energy in the ultraviolet range and beyond. This theoretical breakdown left scientists in a state of despair, as Planck himself described it. Max Planck, a physicist deeply rooted in fundamental principles like entropy and Maxwell's equations, confronted this dilemma. He reluctantly introduced a radical idea. Rather than light energy being continuous, it was parceled into discrete units, or quanta, each scaled by its frequency. This meant energy could only exist in specific quantized amounts, expressed by the formula E equals hv, where E is energy, V is frequency, and H is Planck's constant. By treating electromagnetic energy as shared among a set of electromagnetic oscillators, Planck's model demonstrated that high-frequency quanta carried higher energy, thus limiting their probable number in any system. This revolutionary statistical approach successfully resolved the ultraviolet catastrophe, accurately describing the observed blackbody spectrum with its characteristic peak. Though Planck initially viewed these quanta as a mathematical construct, his groundbreaking formulation planted the seed for quantum theory, fundamentally reshaping our understanding of the universe. Evidence of this universal principle can even be found in the cosmos, where the faint glow of the cosmic microwave background radiation, the afterglow of the Big Bang, perfectly matches a blackbody spectrum. Chapter 24. Photoelectric Effect. At the turn of the 20th century, physicists grappled with the mystery of the photoelectric effect. Ultraviolet light produced an electric current in metals, while even intense red light did not. It seemed a threshold amount of energy was required to dislodge electrons from the metal surface, yet the mechanism remained unknown. In 1905, Albert Einstein unveiled a groundbreaking solution, later earning him a Nobel Prize. Building on Max Planck's concept of energy quanta, Einstein proposed that light itself consists of discrete energy packets, or photons. Each photon carries a specific amount of energy, directly proportional to its frequency. He suggested that individual photon bullets strike electrons, transferring their energy. This explained why blue or ultraviolet light with higher frequency photons possessed enough energy to eject electrons, while lower-frequency red photons, regardless of their quantity, brightness, simply did not. This radical idea introduced the profound concept of wave-particle duality, suggesting light behaves as both a continuous wave and a stream of particles. Subsequent experiments, including clever variations of the double-slit experiment, confirmed this bizarre reality. Light, and later even matter particles, like electrons and molecules, can act as both waves and particles, depending on how they are observed. This effect finds practical application today in technologies like solar cells, where light liberates electrons from semiconductor materials to generate electricity. 25. Schrödinger's wave equation. Building on the idea that particles and waves are deeply interconnected, Erwin Schrödinger devised a landmark equation in 1926 to describe the probability of a particle's location while it behaves as a wave. This solved the conundrum of how discrete particles could manifest as continuous waves. Prior to this, Niels Bohr had advanced the concept of quantized energy, suggested by Max Planck, to explain electrons existing in specific energy shells within atoms, much like planets in distinct orbits. This model successfully accounted for the characteristic light spectra of elements, acting as unique atomic fingerprints. However, Bohr's model struggled with more complex atoms and the wave nature of electrons. Schrödinger's pivotal contribution was the wave function, a statistical expression containing all knowable information about a particle's probable location. This probabilistic framework not only refined the understanding of electron orbitals, revealing complex, non-spherical shapes, but also extended the wave-particle duality to all matter, fundamentally establishing quantum mechanics and ushering in modern chemistry. 26. Heisenberg's uncertainty principle. Heisenberg's uncertainty principle reveals a fundamental limit in knowing the subatomic world. A particle's precise position and its momentum, or speed, cannot be simultaneously determined. The more accurately one is measured, the less precisely the other can be known. This isn't an instrumentation flaw, but an intrinsic aspect of quantum mechanics. The act of observation itself creates this uncertainty. To pinpoint a neutron's position, high-energy photons are required, yet these photon bullets impart a significant kick, unpredictably altering the neutron's speed. Conversely, using gentler, lower-energy photons to minimize velocity changes means longer wavelengths, thus degrading position accuracy. This inherent interaction, linked to wave-particle duality, precludes simultaneous exact measurements. This principle shattered classical determinism, which presumed a universe where all events were predictable. Quantum mechanics instead posits that a particle's path isn't fixed until observed, and its future behavior is fundamentally probabilistic, not certain. This profound shift from predictable cause and effect to inherent chance, challenging even Albert Einstein, moved physics into abstract mathematical descriptions. 27. Copenhagen interpretation. Niels Bohr's Copenhagen interpretation emerged as a unifying framework for quantum mechanics, profoundly asserting that the observer plays an essential role in defining reality. It reconciled Erwin Schrödinger's wave equations with Werner Heisenberg's uncertainty principle, suggesting that rather than being separate phenomena, wave and particle behaviors are complementary aspects of the same underlying reality. Just as a visual illusion can appear as two different images depending on one's focus, quantum entities manifest as either a wave or a particle based on how they are observed. Bohr advanced the idea that the act of observation is not a detached, passive process, but an integral part of the quantum system. He contended that the observer's intervention inherently fixes the outcome of quantum experiments, rather than simply disturbing an existing state. This revolutionary concept of observer participation fundamentally challenged the long-held ideal of scientific objectivity, suggesting that the subatomic world is inherently unknowable in its unobserved state. When a measurement is made, the quantum system's multiple potential states collapse into a single definite outcome, making the observer's choice of measurement an active participant in how reality manifests. The Copenhagen interpretation thus calls for a new understanding of reality, where the strange and unfamiliar nature of the quantum realm must be accepted on its own terms, free from classical assumptions. 28. Schrödinger's cat. Imagine a cat sealed in a box, its very existence hanging in a bizarre quantum balance, both alive and dead simultaneously. This unsettling scenario, known as Schrödinger's cat, was conceived by physicist Erwin Schrödinger to highlight what he saw as the preposterous implications of the Copenhagen interpretation of quantum theory. According to Copenhagen, subatomic systems don't exist in a defined state, but rather as a cloud of probability or superposition of all possibilities. Only upon observation does this wave function collapse, forcing the particle into one concrete reality. Schrödinger, in 1935, challenged this by applying it to the macroscopic world. His hypothetical setup places a cat in a sealed chamber with a radioactive substance. If an atom decays, a Geiger counter triggers, releasing poison, killing the cat. There's a 50-50 chance of decay. Following Copenhagen's logic, while the box remains closed, the cat isn't merely likely to be alive or dead, it exists in a bewildering blend of both. Schrödinger found this ridiculous. A cat is either one or the other, not a fuzzy mixture. What makes an observer? Must it be conscious? Does a holiday home in the woods exist as a superposition of burned down or perfectly fine until we see it? One radical response is Hugh Everett's many worlds hypothesis. It suggests that every quantum measurement splits the universe into parallel realities. In one, the cat is alive. In another, it is dead. This avoids the observer paradox, but at the cost of countless branching universes for every possibility. Ultimately, Schrödinger's thought experiment remains a powerful tool for pondering quantum reality's peculiar nature. Some physicists now argue that applying classical common sense to the inherently strange quantum realm simply misses the point, urging us to accept its unique terms. Chapter 29. The EPR Paradox. Albert Einstein challenged the prevailing Copenhagen interpretation of quantum mechanics, which posited that quantum systems exist in a probabilistic blend of all possible states until observed. He, along with Boris Podolsky and Nathan Rosen, articulated their discomfort in the 1935 Einstein-Podolsky-Rosen EPR paradox. They imagined a particle decaying into two smaller ones, whose properties, like spin, must be opposite due to conservation laws. If one particle's spin is measured, the other spin is instantaneously known regardless of distance. This spooky action at a distance implied information traveled faster than light, or that a measurement on one particle immediately influenced another far away, an idea Einstein found absurd, preferring a local reality, where particles had fixed properties from the start. However, experiments, particularly those testing Bell's inequalities, have definitively shown that quantum entanglement is a real phenomenon, refuting Einstein's local reality, and demonstrating that particles can remain interconnected across vast distances. This profound discovery has shifted from philosophical debate to practical application. Quantum information, encoded in qubits that can exist in multiple states simultaneously, forms the basis of quantum computing. Entanglement also underpins quantum cryptography, where linked encryption keys change if intercepted, and quantum teleportation, which involves transferring a quantum state, information, from one particle to another using entanglement rather than physically moving matter. This understanding reveals a universe not of independently fixed objects, but a dynamic sea of information where observation plays a fundamental role in shaping reality. Chapter 30: Pauli's Exclusion Principle. The Pauli exclusion principle is a fundamental tenet of quantum mechanics that explains the very solidity and impermeability of matter, why we don't sink through floors or pass our hand through a solid table. Proposed by Wolfgang Pauli, this principle states that no two identical particles, known as fermions, which include electrons, protons, and neutrons, can simultaneously occupy the same quantum state, defined by a unique set of 4 quantum numbers. This rule profoundly influences how particles, particularly electrons, are organized within atoms. Rather than all falling into the lowest energy level, electrons are compelled to fill distinct energy shells, progressively occupying higher states as an atom's electron count increases. This phenomenon is akin to filling seats in a theater from the stage backward, ensuring each electron has its own unique seat. This intrinsic resistance to being compressed into the same quantum state generates what is called degeneracy pressure, providing atoms with their characteristic rigidity. The principle's implications extend to the most extreme objects in the universe. In stellar remnants like white dwarfs, electron degeneracy pressure is the force that prevents further gravitational collapse, allowing a star's mass to be compressed into a dense, Earth-sized body. For even more massive stars, gravity overwhelms electron degeneracy, forcing electrons and protons to merge into neutrons. The resulting neutron stars are then stabilized by the even stronger neutron degeneracy pressure, packing several solar masses into a sphere merely kilometers across. In contrast, particles known as bosons, such as photons, do not obey the exclusion principle. Multiple bosons can inhabit the same quantum state, leading to phenomena like laser light. Thus, Pauli's exclusion principle is not just a theoretical concept. Its consequences are palpable, dictating the very nature of matter and the most dramatic cosmic structures. Chapter 31: Superconductivity. At incredibly low temperatures, some materials achieve superconductivity, a state where they conduct electricity with absolutely no resistance. Discovered in 1911 by Heike Onnes, this phenomenon allows electrical currents to persist for billions of years, essentially achieving a form of perpetual motion. This frictionless flow is explained by the BCS theory, which posits that electrons form linked Cooper pairs. These pairs behave as bosons, allowing them to occupy the same minimum energy state and move cohesively through the material's atomic lattice without collision, much like a superfluid, a liquid with zero viscosity. Relatedly, Bose-Einstein condensates demonstrate similar macroscopic quantum behavior in ultra-cold bosons. The 1980s saw the emergence of high-temperature superconductors, ceramic materials that operate at significantly warmer, though still cold, temperatures. These advancements hold revolutionary potential for powerful electromagnets in MRI scanners and particle accelerators, and could one day enable highly efficient power transmission and magnetic levitation. Chapter 32. Rutherford's Atom. For centuries, atoms were envisioned as the smallest, indivisible particles of matter. However, early 20th century physicists unveiled a more complex reality, probing the inner structure of these fundamental building blocks. The initial breakthrough came with J.J. Thomson's 1887 discovery of the electron, a negatively charged particle. This led to his plum pudding model in 1904, which depicted the atom as a sphere of diffuse positive charge with electrons embedded within it, much like raisins in a pudding. In this view, both positive and negative charges were spread throughout the atomic volume. This model was dramatically challenged by Ernest Rutherford's gold foil experiment in 1909. When heavy alpha particles were fired at a thin gold sheet, most passed through, but a small fraction ricocheted back sharply. This astonishing result, likened by Rutherford to firing a cannonball at tissue paper only to have it rebound, indicated that atoms harbored a tiny, dense, positively charged core, which he termed the nucleus. This revelation marked the birth of nuclear physics. Rutherford later identified the proton, the positively charged particle found within the nucleus. The understanding of atomic structure evolved further with the discovery of isotopes, forms of an element with differing weights, like carbon-12 and carbon-14, due to varying numbers of neutral particles. Carbon-14's predictable radioactive decay, characterized by its half-life, became the basis for radiocarbon dating. In the early 1930s, James Chadwick identified the neutron, a neutral particle with a mass similar to the proton. This refined atomic model established that the nucleus consists of both protons and neutrons, collectively called nucleons, while electrons orbit outside. For example, a carbon-12 atom holds 6 protons and 6 neutrons in its nucleus, surrounded by 6 orbiting electrons. The incredible density of the nucleus, hundreds of thousands of times smaller than the atom itself, presented a puzzle. How do multiple positively charged protons remain bound together, overcoming their mutual electrostatic repulsion? The answer lies in the strong nuclear force, a new fundamental force proposed by Hideki Yukawa. This force acts only over extremely short distances within the nucleus, but is immensely powerful, locking nucleons together at a precise separation. It is one of the 4 fundamental forces, alongside gravity, electromagnetism, and the weak nuclear force. Radioactive substances possessing unstable atomic nuclei emit 3 distinct types of radiation. Alpha particles, heavy helium nuclei, are easily stopped. Beta particles are high-speed electrons, which penetrate further. Gamma rays, electromagnetic waves with no mass but high energy, require dense shielding like lead or concrete. 33. Antimatter. Matter's curious mirror image, where particles possess reversed charges and quantum properties, was theoretically predicted by Paul Dirac in the 1920s. His equations for electrons hinted at the possibility of negative energy states, leading to the concept of these complementary particles. Experimental confirmation arrived in 1932 when Carl Anderson identified positrons, anti-electrons with a positive charge, among cosmic ray particles. Since then, physicists have created antiprotons, antineutrons, and even entire antihydrogen atoms, demonstrating antimatter is a tangible aspect of our universe. The most dramatic characteristic of antimatter is its interaction with ordinary matter. They undergo mutual annihilation in a brilliant flash of pure energy, converting all their mass into energy, according to Einstein's iconic equation E equals mc squared. This destructive process explains why the cosmos is not teeming with equal parts matter and antimatter. Scientists posit that during the Big Bang, a minuscule imbalance occurred, approximately 1 extra matter particle for every 10 billion antimatter particles. This slight excess of matter survived the initial catastrophic annihilations, forming the stars, galaxies, and life we observe today. Antimatter also reveals profound symmetries underpinning physical laws. Mathematically, antiparticles can be conceptualized as normal particles traveling backward in time. Other symmetries include charge conjugation, where all charges are reversed, and parity, which relates to motion through space. While parity symmetry typically holds, it can be broken, as seen with neutrinos, which exist only in a left-handed form. Crucially, subtle violations of combined charge parity, CP, are believed to be the mechanism that allowed matter to dominate over antimatter, potentially involving hypothetical particles called X-bosons. This understanding, while explaining our existence, also raises the distant prospect of proton decay, suggesting that even the matter of our universe might eventually dissipate over timescales vastly longer than its current age. 34. Nuclear fission. The exploration of nuclear fission represents both a monumental scientific achievement and a profound ethical challenge. Its discovery revolutionized our understanding of the atom and ushered in the era of atomic energy. Yet its initial deployment in nuclear weapons inflicted immense devastation and ignited a persistent global proliferation concern. The early 20th century unveiled the atom's intricate structure: electrons orbiting a nucleus composed of protons and neutrons bound by the strong nuclear force. Scientists began to pursue the elusive goal of harnessing the immense energy within the nucleus. While early experiments in 1932 by Cockcroft and Walton demonstrated nuclear transformations, they required more energy input than they produced, leading many to doubt commercial viability. However, in 1938, Otto Hahn and Fritz Strassmann, bombarding uranium with neutrons, unexpectedly observed lighter elements, signaling that the uranium nucleus had split. Lise Meitner and her nephew Otto Frisch quickly recognized that this fission released significant energy because the resulting fragments possessed less overall mass energy. This understanding paved the way for Leo Szilard and Enrico Fermi to conceive of a self-sustaining nuclear chain reaction, which Fermi successfully achieved in 1942 beneath a Chicago stadium. Controlled chain reactions form the basis of nuclear power plants, where boron rods regulate neutron flow and coolants manage heat. France, for instance, generates over 70% of its electricity this way. However, fission also produces radioactive waste, some of which remains hazardous for hundreds of thousands of years, posing complex disposal challenges. Concerned about the potential for nuclear weapons, Szilard and Albert Einstein alerted President Roosevelt. Following a British calculation on bomb feasibility and the attack on Pearl Harbor, the U.S. launched the top-secret Manhattan Project, led by J. Robert Oppenheimer from Los Alamos. The project developed two bomb types: the gun method using enriched uranium-235, like Little Boy, and the implosion method involving plutonium-239, like Fat Man. These devastating weapons were deployed on Hiroshima and Nagasaki in August 1945, causing immediate and long-term casualties numbering in the hundreds of thousands. 35. Nuclear fusion. Nuclear fusion, the fundamental process merging light atomic nuclei to form heavier ones, is the engine behind all the elements around us and the immense energy output of stars like the Sun. This stellar cookery begins by forcing hydrogen nuclei to fuse into helium, releasing vast amounts of energy. Gradually, through successive fusion reactions, all the diverse elements in the universe are forged. Achieving fusion on Earth is exceptionally challenging, requiring extreme temperatures and pressures to overcome the natural repulsion between positively charged protons within nuclei. While lighter hydrogen isotopes, deuterium and tritium, present the lowest energy barrier, initiating their fusion still demands hundreds of millions of kelvins. Scientists are striving to replicate these stellar conditions in fusion reactors, viewing it as the holy grail of clean energy. Fusion power promises significant advantages over nuclear fission, including minimal waste and no greenhouse gas emissions, using readily available fuel. However, current terrestrial efforts consume far more energy than they produce, and controlling the superheated plasma for sustained periods remains a formidable hurdle, as seen in projects like the International Thermonuclear Experimental Reactor. The universe's first stars faced a unique challenge, initially lacking heavier elements to aid in cooling, which complicated their gravitational collapse and ignition. Despite the complexities, harnessing this stellar power on Earth offers a transformative solution to our energy needs. Chapter 36: Standard Models. While familiar protons, neutrons, and electrons might seem like matter's fundamental building blocks, they represent only a glimpse into the vast realm of particle physics. Protons and neutrons themselves are composed of even tinier quarks. Electrons have their ethereal neutrino partners, and the very forces that govern interactions are conveyed by a diverse family of bosons, including light-carrying photons. The Standard Model of particle physics offers a comprehensive framework, bringing together this intricate particle zoo into a unified theoretical family tree. The journey to uncover these constituents began in earnest in the early 20th century. Initially, atoms were understood as a nucleus of protons and neutrons orbited by electrons. However, observations like the sun's fusion processes and the radioactive decay of neutrons hinted at the existence of new, elusive particles, like the neutrino, whose presence was inferred decades before its actual detection. This excavation gradually expanded the known particle collection, revealing a deeper substructure to matter. Within the Standard Model, fundamental particles are categorized into three main types. Hadrons, such as protons and neutrons, are composite particles made from quarks. Quarks possess unusual properties. They come in 6 flavors: up, down, strange, charm, top, bottom, and 3 colors. These color charges dictate the strong nuclear force mediated by gluons, which are so powerful they confine quarks permanently within hadrons, preventing them from existing in isolation. Leptons form the second class, including electrons and their heavier counterparts, muons and taus, each with a corresponding, nearly massless, chargeless neutrino. The third class consists of bosons, the force-carrying particles, like photons, electromagnetic force, and gluons, strong nuclear force, along with W and Z particles, weak nuclear force. Our understanding of this subatomic world largely stems from particle smashing. Physicists utilize massive particle accelerators to propel particles to immense speeds, then collide them either into targets or opposing beams. By observing the debris, the shards of these collisions, and tracking their paths through magnetic fields, scientists can deduce the properties, charge, mass of newly created or liberated particles. Each particle leaves a unique signature, allowing physicists to piece together the universe's most minute components. Despite its incredible success, the Standard Model remains incomplete. Gravity and its hypothesized force-carrying particle, the graviton, are not yet integrated into this otherwise unified theory. 37. Feynman diagrams. Feynman diagrams are an ingenious visual lexicon designed to simplify and represent the intricate mathematics of particle physics interactions. Devised by physicist Richard Feynman, these sketches serve as a potent shorthand for complex quantum equations. Each fundamental interaction is depicted as a vertex, a point where three lines converge. Two straight arrows representing incoming and outgoing particles, with time typically flowing to the right, and backward arrows for antiparticles. And a wavy or squiggly line signifying the mediating force-carrying particle, such as a photon. More elaborate interactions are constructed by combining multiple such vertices. Beyond their role as a clear visualization tool, Feynman diagrams are crucial for calculating the probabilities of these interactions occurring. Physicists achieve this by mapping out all possible variations of a given interaction, allowing for a comprehensive assessment of likelihoods. This powerful graphical notation was foundational to the development of quantum electrodynamics, QED, a theory describing electromagnetic interactions, and has since been extended to encompass other fundamental forces like the strong nuclear force, quantum chromodynamics, and the unified electroweak force. These diagrams must always adhere to fundamental conservation laws, ensuring energy and charge are preserved throughout the interaction. 38. The God particle. In 1964, physicist Peter Higgs conceived a groundbreaking idea to explain why particles possess mass. He proposed the existence of a pervasive Higgs field through which particles interact, thereby acquiring their apparent heft. This concept resolved a critical discrepancy in physics: why some fundamental force carriers, like photons, are massless, while others, such as W and Z bosons, are incredibly heavy, despite unified theories suggesting they should be similar. Visualize attempting to move through a viscous liquid. The resistance slows you, imparting a sensation of greater mass. Similarly, particles traversing the Higgs field experience varying degrees of interaction, effectively manifesting as different masses. The stronger the interaction, the greater the mass. The Large Hadron Collider at CERN is actively searching for the Higgs boson, the particle that mediates this field. Its detection, or its absence, remains the crucial missing link in the Standard Model, with profound implications for our understanding of the universe's fundamental constituents and the origins of mass itself. 39. String theory. Driven by a quest for deeper understanding beyond the Standard Model, physicists explore string theory, an idea that fundamentally recasts the nature of particles. Instead of viewing quarks, electrons, and photons as indivisible points, string theory proposes they are tiny, vibrating, one-dimensional strings. The unique properties of each particle, its mass, charge, or associated energy, are determined by the specific patterns of these vibrations, much like the distinct harmonic tones played on a musical string. To accommodate the mathematics of these vibrating strings, the theory posits the existence of more dimensions than our familiar four, 3 spatial, 1 temporal, suggesting up to 10 or 11 total, with the additional dimensions curled up and imperceptible to us. It is within these unseen realms that the particle strings oscillate. M-theory, an extension, generalizes this concept to include higher-dimensional branes beyond just strings. String theory's ambition is profound: to be a theory of everything, a singular framework unifying all fundamental forces, including gravity, which famously eluded Einstein. However, this elegant, entirely mathematical construct faces a significant challenge: the current absence of experimental evidence or falsifiable predictions. Critics, referencing Karl Popper's philosophy of science, question its scientific status, leading to ongoing debate. Despite these hurdles, its mathematical beauty and unifying potential continue to inspire researchers seeking to uncover the universe's deepest, most fundamental harmonies. 40. Special relativity. While Newton's laws effectively chart the motion of everyday objects, Albert Einstein's 1905 special relativity revealed profound effects for objects nearing the speed of light. At such extreme velocities, observers perceive objects becoming heavier, contracting in length, and experiencing time more slowly. This occurs because nothing can exceed light's universal speed limit, demanding distortions in space and time themselves. 19th-century physicists initially posited an ether as a medium through which light waves propagated. However, the pivotal 1887 Michelson-Morley experiment disproved its existence. Light speed remained constant, irrespective of an observer's motion, a striking invariance that became Einstein's foundational insight. He reasoned that if light's velocity is absolute, then space and time must distort to reconcile different viewpoints at high speeds, creating a four-dimensional spacetime. To uphold light as the ultimate speed, distances shrink and time slows down for objects approaching it, famously illustrated by the twin paradox, where a spacefaring sibling ages less. Einstein declared all motion relative, asserting there is no absolute fixed reference frame. Within inertial frames, spaces moving at constant speeds relative to one another, physical laws remain consistent. This relativity, particularly the phenomenon of time dilation, was empirically confirmed in 1971 when atomic clocks flown around the world registered fractional time differences in precise agreement with special relativity's predictions. The theory also predicts that an object's mass increases exponentially as it nears light speed, ultimately requiring infinite energy and preventing anything with mass from ever achieving light speed. Chapter 41. General Relativity. General relativity revolutionized our view of space and time by integrating gravity into Einstein's earlier work. His foundational insight began with recognizing that a person in free fall experiences weightlessness, effectively not feeling gravity's pull. This led to his happiest thought that acceleration is physically equivalent to gravity. From this equivalence principle, Einstein formulated general relativity, proposing that gravity is not merely a force, but a consequence of mass distorting the four-dimensional fabric of spacetime. Conceptualize spacetime as a flexible rubber sheet where massive objects, like planets or stars, create depressions. These warps then guide the movement of other objects, demonstrating gravitational pull and orbital paths. This distortion also bends light rays passing near massive bodies, an effect known as gravitational lensing, visibly creating arcs, or Einstein rings, from distant galaxies. The theory further predicts extreme phenomena such as black holes, which are inescapable wells in spacetime, and the existence of gravitational waves, ripples propagating through spacetime itself from energetic cosmic events. Despite its profound success and observational confirmations, unifying general relativity with quantum theory remains an elusive frontier, a challenge that continues to puzzle physicists. Chapter 42. Black holes. Black holes represent regions of spacetime where gravity is so overwhelmingly intense that nothing, not even light, can escape their pull. This extreme condition arises when an object's escape velocity, the speed needed to break free, surpasses the speed of light itself. Once conceived as frozen stars, these colossal gravitational wells are now understood as singularities or profound distortions in Einstein's spacetime fabric. They vary in size, from the supermassive entities anchoring the centers of galaxies, including our own Milky Way, to smaller remnants left behind by dead stars. The critical boundary beyond which nothing can return is known as the event horizon. Cross this invisible threshold, and one is irresistibly drawn into the black hole. The immense gravitational gradient within, particularly in smaller black holes, leads to a phenomenon colloquially termed spaghettification, where an object is stretched and torn by varying gravitational forces acting on different parts of its body. Intriguingly, theoretical predictions by Stephen Hawking suggest black holes are not entirely black. They slowly evaporate over vast timescales by emitting Hawking radiation, a quantum effect where particles escape their grasp. Despite their light-trapping nature, black holes are detectable through indirect means. Their presence is inferred by observing the powerful gravitational influence they exert on nearby stars and gas, causing them to orbit erratically. Infalling gas can also heat up to incredible temperatures, emitting intense X-rays, or even powering the most luminous objects in the universe, known as quasars. Theorists also ponder the existence of wormholes, hypothetical tunnels through spacetime that could connect disparate regions or even different universes, offering a sci-fi vision of cosmic shortcuts, though these remain speculative. Chapter 43, Olbers' Paradox. Have you ever gazed at the night sky and simply accepted its darkness? This seemingly obvious observation actually holds one of cosmology's most profound secrets. Olbers' paradox asks a simple yet powerful question. If the universe is infinitely vast and has existed forever, populated by countless stars, why isn't the entire night sky blazing with light, as bright as the surface of the sun? The premise is straightforward. In an endless, eternal cosmos, every line of sight should eventually intercept a star. Imagine standing in an incredibly dense forest. Eventually, every direction you look would be blocked by a tree. Even if distant stars appear dim individually, the sheer number of them at greater distances should add up, illuminating the sky uniformly. Yet our night sky is decidedly dark. This paradox, first noted by Johannes Kepler and formally articulated by Heinrich Olbers, paved the way for our modern understanding of the universe. The solutions reveal fundamental truths about cosmic reality. Firstly, the universe is not infinitely old. It began a finite time ago. Light from the most distant stars simply hasn't had enough time to reach us. When we look far into space, we are looking back in time, and the universe beyond a certain point has not yet switched on for our observation. Secondly, the universe is not infinitely static, it is expanding. This expansion causes the light from distant galaxies to be redshifted, stretching its wavelengths and making these light sources appear fainter and redder, eventually shifting them out of the visible spectrum entirely. This phenomenon, coupled with the fact that stars themselves have finite lifetimes, means there simply aren't enough stars in our observable universe active for long enough to saturate the night sky with light. Thus, the dark night sky isn't a void, but a cosmic canvas reflecting a universe with a definite beginning, an ongoing expansion, and a finite age. 44. Hubble's Law. Astronomer Edwin Hubble profoundly reshaped our understanding of the cosmos by revealing that galaxies beyond our own are not static neighbors, but are uniformly moving away from us. He discovered that the speed at which these celestial bodies recede is directly proportional to their distance from us, a fundamental principle now known as Hubble's law. This astounding finding provided the initial, compelling evidence that the universe itself is not static, but in a state of continuous expansion, drastically altering humanity's view of its place within the vastness of space. Hubble's groundbreaking work in the 1920s settled a fierce scientific debate about the true scale of the universe. Using the powerful 100-inch Hooker telescope, he meticulously measured the distances to various spiral nebulae, notably the Andromeda Galaxy. using flickering Cepheid variable stars as reliable cosmic yardsticks. His measurements proved these nebulae were, in fact, island universes, vast galaxies far beyond the confines of our Milky Way. Further observations showed that light from these distant galaxies was significantly redshifted, akin to the changing pitch of a receding ambulance siren. This redshift confirmed that galaxies were actively rushing away from Earth, with the most distant ones accelerating the fastest. This phenomenon is best visualized as spots on an inflating balloon, where every spot moves further from every other spot, indicating a universal expansion rather than a special status for our location. The constant ratio of a galaxy's speed to its distance is known as the Hubble constant. Accurately measuring this constant, a task still undertaken by instruments like the Hubble Space Telescope, is crucial for determining the age of the universe, which is estimated to be approximately 14 billion years. This ongoing expansion means the cosmos exists in a delicate balance, poised between eternally scattering into nothingness and eventually collapsing back in on itself. Chapter 45. The Big Bang. The universe originated about 14 billion years ago in the Big Bang, a colossal event that birthed all space, time, and matter from an incredibly hot, dense point. Though initially mocked by British astronomer Fred Hoyle, who coined the term in ridicule, this theory is now overwhelmingly supported by scientific evidence. A primary piece of evidence is Edwin Hubble's 1920s observation of an expanding universe, where galaxies recede from each other. This expansion stretches light waves, causing a redshift that helps astronomers gauge cosmic distances. Crucially, the early universe's extreme heat during its first minutes facilitated nucleosynthesis, forming precise proportions of light elements like hydrogen, helium, deuterium, and beryllium. These predicted abundances match current astronomical measurements. The 1965 discovery of the cosmic microwave background, CMB, radiation constitutes another major pillar. This faint, omnipresent microwave glow is a remnant from roughly 380,000 years post-Big Bang, when the cooling universe allowed atoms to form, clearing the fog and letting light travel freely. This ancient glow, redshifted by expansion, is now just 2.7 Kelvin. Cosmologists ponder the universe's ultimate fate: a big crunch if gravity wins, a big chill if expansion prevails, or a Goldilocks universe of perpetual, slowing expansion, which current data suggests is most likely. The question of what preceded the Big Bang is complex, as space-time itself originated then, though concepts like M-theory explore related ideas within higher dimensions. 46. Cosmic inflation. The observable universe presents several profound puzzles. Its remarkable flatness, where parallel light rays remain parallel over vast distances. The horizon problem, which questions why distant, causally disconnected regions appear uniformly consistent. And its overall smoothness, showing an even distribution of galaxies rather than extreme clumping. These characteristics imply a precisely balanced and coherent cosmos. Cosmic inflation, theorized by Alan Guth, provides a unified answer. It posits that immediately after the Big Bang, around 10 to the negative 35 seconds, the universe underwent an extraordinarily rapid exponential growth spurt. This inflation, expanding faster than light, effectively smoothed out initial quantum fluctuations, much like stretching a wrinkled surface, thereby establishing the observed uniformity and flatness. This rapid phase set the precise conditions for the universe's subsequent slower expansion, leading to the structured cosmos we observe. Though its specific mechanism is still under investigation, inflation is a cornerstone of modern cosmological understanding. Chapter 47, Dark Matter. Though much of the universe glows with stars and reflected light, an immense unseen component, dark matter, makes up the majority of its mass. This mysterious substance is undetectable through light because it neither emits nor reflects it, yet its profound gravitational influence shapes the cosmos. Instead of direct observation, its presence is inferred by its powerful tug on visible objects, much like an unseen companion whose gravity subtly alters the orbit of a visible body. Early clues surfaced in the 1930s when astronomer Fritz Zwicky observed galaxy clusters whose gravitational effects vastly outstripped their visible stars and gas. Later, the unexpectedly rapid rotation of outer gas in spiral galaxies confirmed this cosmic discrepancy, revealing galaxies possess far more mass than their luminous content suggests. This extra dark mass appears to envelop galaxies in vast spherical halos. This exotic dark matter accounts for about 23% of the universe's energy budget, profoundly dictating its fate. It provides the precise gravitational pull necessary for the universe's expansion to gradually slow but never entirely halt, maintaining a delicate balance. Scientists propose two main categories for dark matter's composition. One possibility is machos, massive compact halo objects, celestial bodies like dark gas clouds, dim stars, or unlit planets. While some machos have been detected via gravitational lensing, where their gravity bends background starlight, causing distant stars to momentarily brighten, their numbers and their baryonic nature, meaning they're made of normal matter, are insufficient to account for the total dark matter. The limited cosmic abundance of primordial deuterium, an isotope formed only in the Big Bang, strongly confirms that the bulk of dark matter cannot be baryonic. This leads to the second, more exotic hypothesis, WIMPs, weakly interacting massive particles. These hypothetical subatomic particles would interact minimally with normal matter or light, making them incredibly elusive and difficult to detect. Neutrinos, though a known WIMP candidate with a tiny mass, don't account for the full deficit. The ongoing intensive search for other exotic particles like axions and photinos represents the cutting edge of physics, promising to unveil one of the universe's deepest and most pervasive secrets. 48. Cosmological constant. Albert Einstein once considered the introduction of his cosmological constant to be his greatest scientific misstep. Originally, he added this term to the equations of general relativity to counteract gravity, aiming to depict a stable, static universe rather than one that would collapse under its own gravitational pull. This repulsive anti-gravity term was purely a mathematical construct, not based on observed phenomena. However, once Edwin Hubble's observations confirmed the expansion of the universe, Einstein promptly abandoned the constant, consigning it to what he believed was historical irrelevance, with its value simply set to 0 in the fundamental equations. Decades later, in the 1990s, a surprising discovery forced a reevaluation. Astronomers studying Type I supernovae in distant galaxies noticed they appeared fainter than expected. These specific supernovae have a consistent intrinsic brightness, making them reliable standard candles for measuring cosmic distances. The faintness implied these distant explosions were further away than predicted by a steadily expanding universe, suggesting instead that the universe's expansion was accelerating. This revelation profoundly shocked the scientific community and necessitated the reintroduction of Einstein's cosmological constant, now assigned a non-zero value of approximately 0.7 to account for this newly observed repulsive force. This mysterious force, which counteracts gravity on large scales, has been named dark energy. Its precise origin remains unknown, but it is theorized to be a form of energy inherent to the vacuum of empty space, exerting a negative pressure that causes regions devoid of matter to inflate. While its strength has been roughly determined from supernova observations and other cosmological data, like the cosmic microwave background, whether it truly is a constant throughout space and time, or if its value changes, a concept sometimes called quintessence, is still an active area of research. The discovery of dark energy has been pivotal in balancing the cosmic energy budget, revealing that the universe is composed of roughly 4% normal baryonic matter, 23% exotic non-baryonic dark matter, and a staggering 73% dark energy. This composition aligns with a Goldilocks universe, poised near the critical density where it is neither open nor closed. Yet the enigmatic nature of dark energy complicates predictions about the universe's ultimate fate. Should dark energy's influence continue to grow, the accelerating expansion will eventually overpower gravity, leading to scenarios where massive structures, galaxies, and even atoms themselves could be torn apart in a big rip. Despite these advances, the universe still holds many secrets, with 95% of its constituents and the true nature of dark energy remaining profound mysteries. 49. Fermi Paradox. The universe's immense age and countless stars prompt a profound question: where are the alien civilizations? This is Fermi's paradox, first articulated by Enrico Fermi in 1950. Given billions of planets, logic suggests life should be common, yet we detect nothing. The Drake equation attempts to quantify the probability of contactable alien civilizations, but its many uncertain variables yield vastly different estimates, from millions to potentially only our own planet. Rigorous searches continue, scrutinizing Martian rocks for microbial traces, planning missions for Europa's subsurface oceans, analyzing distant exoplanets for chemical biosignatures, and SETI's tireless scanning for structured radio signals. Yet, despite these extensive efforts, the cosmos remains eerily silent. Even unique discoveries like pulsars have natural explanations. Explanations for this pervasive quietude vary. Perhaps intelligent life is inherently short-lived, self-destructing before interstellar communication. Perhaps other civilizations deliberately choose to avoid contact, or simply they are too preoccupied to make their presence known. 50. Anthropic Principle. The anthropic principle proposes that the universe's fundamental constants and forces are precisely as they are because if they were different, observers like us could not exist to witness it. This idea addresses the apparent fine-tuning of the cosmos, where tiny variations in parameters, such as nuclear forces, dark energy, or particle masses, would render the universe uninhabitable, preventing the formation of atoms, stars, or complex life. Rather than suggesting humanity is uniquely special, the principle posits a selection effect. We necessarily find ourselves in a universe conducive to our existence. The weak anthropic principle states that our presence restricts the possible properties of the universe we observe. A stronger version suggests that the universe must produce life, perhaps requiring observers to manifest its quantum reality. The concept of a multiverse, where countless parallel universes exist with differing physical laws, offers a resolution, implying that our life-sustaining universe is simply one among many, not an improbable cosmic accident. While critics view it as a truism or prefer purely mathematical explanations for cosmic parameters, the anthropic principle prompts profound philosophical reflection on our place within the vastness of existence. That wraps up our exploration of today's book. If even one idea here gave you something to reflect on, give it a like so YouTube knows to share more with you. And if you'd like the next insight in your feed, hit subscribe. Remember, what you heard today is our independent interpretation, enriched with analysis and exercises. The full book has far more depth, so consider reading it to experience the author's work directly. Thanks for listening to Def 2 Insights, where we turn great books into tools for growth.